had he not asked about that question, I would left in my bag and just all along the thermo stuff. But Cornish was really cool about it. He was like, yeah, like, I gave him notes, and he gave me his notes, he doesn't give out, he gave me his notes, and he gave me his textbook, so it's really an exam on Tuesday. Yeah, it's just,
you don't already start? Jesse, have you started the quantum yet? No. I'm telling you, you want my help, it can't be at 10 o'clock the night before. Definitely not.
Cheers.
Due Tuesday?
Yeah, this is our last homework in quantum.
Probably the weekend then.
Can you finish it? Are you allotting at least an hour?
it turns out well.
That makes sense to me. I made my mind on that.
Oh, I know why he hasn't been able to find me. I haven't tagged them. They're probably really hard to search for.
Or he doesn't know how to use YouTube very well.
Now, go with that. It's got to be negative when the angle is small.
Yeah. I mean,
so
when
there's a minus sign here.
it's got to be negative when tangent theta theta t is theta I plus theta t is greater.
I just glanced through your homework solutions and realized that some people missed a clue a couple of classes ago, which was that when I told you what the reflection coefficient was for p-polarized light, so that's light with electric field in the plane of incidence. So that. Then we first have to think about, remember we're taking the amplitudes and directions of these fields, and then it's always a question of which way we define to be positive for the electric field, right? So for the incident field, we're defining that to be positive. For the reflected field, it depends upon which textbook, how the sign is defined. But what we know is that the incident field, let's say a normal incidence, let's start with normal incidence, points that way, for example, at a particular instant in time, right? The field inside the surface is smaller because this has got dielectric constant, so the field is going to be weaker, right? And that means that the only way that all these fields can add up is if this field points in the opposite direction from that field. And some textbooks take that direction to be the positive direction for the reflected field, and others take the other direction to be the positive direction for the reflected field. And that'll put a minus sign there or not. Okay? So this could have a minus sign or it could not have a minus sign, depending upon the definition of the directions of the field. I'll take it out for a moment because what we want to do is decide whether the sign of this reflection coefficient changes. And if the sign changes, that's the same as multiplying the field by -1, which is e to the I pi. So that's a phase change of pi when the field changes by a factor of -1, right? When the reflection coefficient changes by a factor of -1. And then we can ask, so you were asked to argue that when you go above or below the Brewster angle, the sign changes as you cross through the Brewster angle. And this argument is actually pretty simple to make, which is that you've got one relationship here, which is that if nt is greater than ni, then the transmitted angle here is smaller than the incident angle due to Snell's law, right? Which means then that this quantity here will be positive for a small incident angle. So if this angle is small, you're near the normal, this quantity will be positive. all right? This quantity here is the sum of those two angles. It's the sum of this angle and the sum of and that angle, okay? For near incident, that angle, that sum is going to be small. And so tangent of theta incident plus theta transmitted is going to be small. It's going to be positive because theta I plus theta t is small, so it will be positive. So it's positive over positive. The reflection coefficient, by that definition that we started out with, is positive. Okay. Then, as we increase this angle, right? Let me just dash home here. Right. Then I'll get a reflected angle that's going to be equal and opposite. And I'm going to get over here, for example, and I'll get an angle like so. And this plus this will be greater than 90 degrees. So when theta I plus theta t is greater than 90 degrees, then tangent becomes negative. Switch sign grows and then becomes negative. So this does not switch signs, but this does when theta I plus theta t is greater than 90 degrees. All right? That will work out that when this angle, because 90 degrees turns out to be the important thing, when this angle here is 90 degrees, that is theta Brewster. So at theta Brewster, theta reflection minus 90 plus, well, in any case, this will turn out to be 90 degrees. And for any larger angle, this angle will be larger than 90 degrees. Is that right? Yeah.
So,
and so the sign will switch when theta Brewster, when the angle between the reflected angle and the transmitted angle is greater than 90 degrees, is equal to 90 degrees, then the sign of the reflection coefficient switches. So that was all you needed to do, yes.
couldn't that simply just be said the Brewster angle condition is theta I plus theta t equals pi over 2?
Yes.
And then say when it's greater than that, less than
Yeah,
that.
but well, when it's greater than that, less than that, but you still need to write this down to prove that the reflection coefficient changes sign.
No, I did that. I mean, but I mean,
Start with that,
your
then-
complex angle's over here. Like the complex argument for the angle's over here.
I was trying to make it clear to everyone in the room, including me. Okay. Now, I haven't looked to see what I've actually posted. Have I posted any notes on traveling charges, on moving charges? Does anyone know? Does anyone look at my notes? Yes. I have not yet posted moving charges. Okay. Did I post the tan theta I minus theta t? Yes. Okay, good.
Is this coming one the last homework?
What?
Is this coming one the last homework, or was this the last homework?
This coming one is the last homework.
I haven't assigned one yet,
Oh,
But we will.
but there will be one.
and that will be. Is that the last one?
Oh, is it the last one? I
Unless you-
don't know.
Unless you have one due.
Let's see, the last class is around May 3rd. Doesn't that mean that I could have two more homeworks?
There's no Thursdays.
Say that again?
There's only one more Thursday.
You could, but the second one.
There's only one more Thursday?
Last day of class is Wednesday.
Yeah.
And that's 13.
Oh, you're right.
Yeah, it's still turning.
So wait, but May 3rd is the May 2nd is a Thursday.
Yeah.
Is May 2nd the Thursday after this one that we're sitting on right now?
1 week from today.
Okay, then there's only one more homework.
And it's not due next Thursday. Yay!
It is due next Thursday.
It is due next Thursday.
Dang!
Yeah, okay. And that'll be on accelerating charges and antennas, I guess. I'm just thinking I don't have anywhere near enough time. So here's the first page of notes, here's the second page of notes.
End of class.
All right. So
I'm just gonna have to tag the heck out of these videos.
I made a statement, and I actually have just decided not to prove it to you, but I'll give you the framework of the argument. Here's where the big hands matter. That if we find, first, this is not a statement that's got to be proven. If I find a vector potential that depends upon the emission time and the observation time, and that we then know, for example, we can write the, we've got some source of radiation. It could just be a single charge moving along, or it could be a current. But I've got some source that's moving along here, and that source, at some instant in time, is at position Tx. About that. No. Won't worry about where it is. I'll want to observe that source. And I'm going to observe it at position Tx. And the radiation that arrives over here had to have left this point over here at a different time, because it takes time for the signal to arrive. So I'll call that point there the source point. That's a point. I'll call that T prime X prime. And that's got to be selected such that that signal arrives there. And we can relate the times pretty easily. We can write down, I think I'll write it over here, set it off to the side, that T prime is equal to T minus X minus X prime, the magnitude, divided by the speed of light. That's how long a signal takes to get from there to there. Okay? And then the question is, for a moving charge, what fields do we actually observe? And in order to find this solution, what we ask is that, of course, the vector potential, the full 4-vector potential, be the solution to the wave equation, subject to appropriate conditions. And the condition that we chose was Lorentz gauge. And we won't come back to that again, I don't think. Right? But we have a relationship that we want to test, which is that 1 over c squared d squared and t squared a mu minus 3 vector del squared a mu. So that's for all the terms, including the electric potential. Right? Is equal to 4 pi over c j mu at t and x. And we have to sort of guess some form for a mu in order to see whether we can satisfy that wave equation. And I've written all of that in the observer's time. Okay? And it gets complicated because the observer's time and position is not the same as the emitter's time and position. And that wasn't a problem when the charge wasn't moving. But if it is moving, then those times and positions are going to be different from one another. We have to make corrections. So we're going to make a guess. The procedure is to make a guess as to what the form of the vector potential is, and then demonstrate that that form of the vector potential actually satisfies that wave equation. And the trick here is in being careful about the way that you take your derivatives, because derivatives would be taken in x, let's say, just for interest's sake, you know, not the prime coordinates, but x and t. And I've got this relationship between the source position, which is x prime and t prime, and the observation position, which is x and t. So we're going to make this guess, and then I'm going to wave my hands and argue that when you actually do everything carefully, it works. So this looks just like the vector potential definition that we had before. I'm afraid that in my notes I casually switch between x vector and r vector. And you're just expected to know that when I write the vector there, I mean it's 3D. And if I attempt to make corrections as I go along, I'm probably going to make a mistake. So you make the substitution that r vector is the same as x vector. Okay? dv prime. What? These are primed coordinates here. This is where the source is. I'm integrating over where the source is. All right? And that's the observation point, and that's the source point. Okay? So this is not so simple because the charges can be moving. Okay? So then what we've actually got to do is we have to rewrite our derivatives to make sure that we're taking care of the fact that a mu at t and r is a function of r prime, t prime, and, well, actually, in the end, it's going to be of t and r. But I want to take a derivative of things that are written in terms of r prime and t prime. I would like, actually, to be able to take my, my derivatives and move them into the integral. Okay? And so we can use this relationship between t and t prime to define the other relationships so that then we can go ahead and take derivatives. All right? The derivatives can be complicated, but here's an easy one. So this is the one that I'll do for you. And that is that dt is equal to dt prime. Okay. All right. So yeah, that one's easy, and we can then, of course, because of this, we can take our derivatives here very easily, right? The time derivatives are easy, okay? But the space derivatives can be complicated, and I'll give you one example of how they get complicated. So, for example, I want to take del A mu, and you just do that term by term. And that's going to be, that is 1 over, del, and now I'll write out a mu of 1 over c integral j mu r prime t prime over r minus r prime dv prime. And I need to find some way of operating del on this difference here, that's r minus r prime, and I've got a relationship between r prime, and t prime. Right? That's given up here. T prime equals to r minus r prime. So I've got a relationship in there that I've got to take care of. One way to do that, now I'll take my del on the inside. 1 over c integral, I can just take it in because those are prime coordinates, right? 1 over r minus r prime, that's that part there, right? Now, I'm going to use a little bit of a trick here, not too bad, which is that, for example, if I want to take the derivative with respect to x of something, I can take it this way. D by dt, dt, dx. Right? Physicists approach. Mathematicians wouldn't do that. Okay? But that's the logic of what I'm about to do. So, this would be d j mu r prime t prime dt prime, and then gradient of t prime. And t prime has got this form here, so there is a gradient for them. Then product rule, I've got to actually take the other derivative. So I have inside the derivative plus j mu gradient 1 over r minus r prime. And all of that dv prime. This was more, actually, just by way of example. Ohanian goes through all of the steps and actually, no, actually he doesn't. But in the notes that I'm going to post, I filled in a lot of the intermediate steps in Ohanian. He tends to be, he's smarter than I am. And he just skips steps because he sees it clearly. I don't. So I have to fill in the steps. So in the notes that I'm posting, I'll fill in steps. But I just wanted to demonstrate here how something that looks like it could be really simple actually can get complicated pretty quickly if you're careful about the coordinates that you're using. All right, maybe I'll do one more example of, let's be careful about the coordinates that we're using. Let's do gradient t prime. And the way that I'm going to do this is actually write it out in 3-vector Cartesian coordinates so that I can figure out what's going on. Okay. Some of you can probably do it in your heads. I can't. That. Okay. Oops. I've already messed up. T prime is r minus r prime over c for the gradient. All right, the t part goes away. Now let me write it all out. X minus x prime squared plus y minus y prime squared plus z minus z prime squared to the 1/2. All right, that gradient's not so bad to take. All right, that would be 1 over c, 1 over r minus r prime times 2 x minus x prime plus I 2 y minus y prime j plus 2 z minus z prime. Okay. Got my 1/2. I took my derivative and ended up with that. Got rid of a minus sign. Probably I have a half in here that I'm missing. Ryan? Yes. Am I missing a half? I think I'm missing a half. When I took the derivative, I brought down to minus 1/2. Yeah. Okay, that's good because then those cancel out. This is r minus r prime. So this is equal to 1 over c r minus r prime over r minus r prime magnitude. Is that right? Yes. Okay. So an example of taking care and then the result of the gradient. So you're taking the gradient of the primed time and you end up with a term.
What happened to the minus sign?
Minus 1.
I got a 1/2. No, wait, you're right. It's there. I dropped it. It's there. Okay? Then you can imagine taking the next derivative, because we're going to need del squared of that. Because when I started over here, I just said gradient of any, but what I've got to actually do is take del squared. So everything that I've done as a quick example here, you've got to do twice. Right? And that's long and complicated. So,
Isn't that what we have Wolfram alpha for?
I don't know how good Wolfram alpha is at keeping track of vector arithmetic. What?
Unless you're paying for it, it's horrible at it.
Yeah. Okay, so tough one.
Brian, you need to do it by hand.
Yeah. Oh, well, no, you don't need to do it by hand. What I'm showing you here is the plausibility of the argument and why it comes out complicated in the end. That when you, I should bracket that off, by the way. All right. When you're sort of going through a stepwise process where each step seems pretty straightforward, and you look at it and say, oh, why isn't that just this simple relationship? You find out that when you're when you include that relationship between t and t prime, things get complicated, right? But it's all, as long as you're careful about it and you keep track of every bit of the calculation that you're doing, you'll come out okay. But I have never been able to do the whole calculation myself without referring to some source, because I always end up making a mistake and dropping a term or two. So I confess to that. For those of you who are more careful and more mathematical than I, can probably do it right. So given that, let's just call it background. The idea that when you do something like take a gradient, it's not quite as simple as you think it is, as you might think it is. Right? Then I will simply state and have the arithmetic in my notes, right, that we can demonstrate that this potential with this definition of t prime gives us, or rather satisfies the wave equation. Okay, so it is a solution. And it's the solution that we're going to use. And what that potential says is that the potential that you see out here, at some point here, right, is the potential that you would calculate if the charge had moved. So it takes a certain amount of time to get from here to there. So I've got my time is equal to time minus, x minus x prime over c, all right? It takes a certain amount of time for the signal to get from here to there. In that time, the particle has moved some velocity times a change in time. Here. All right? The particle has moved to there. Actually, I take it back. That's v times x minus x over c is how far the particle has